Hey there, this is Math 7 Unit 8, Lesson 8, Keeping Track of All Possible Outcomes. So we're exploring some sample spaces for the experiments that have multiple parts. So lots of different things can happen here as we look through these. So we begin with, first of all, a thing called how many different meals. So how many meals are possible if each meal includes one main course, one side dish, and one drink? So this is a question of how many different possible combinations of meals can you make when these are your options there. And so when you think about this, there's different ways that you can set this up, and we'll look at that really here in activity 2 about making lists, making tables, and making what we call trees. But we'll get there in a second. So what you want to do is you want to think through all the different ways that you can combine these elements to have one of each thing. Okay, so if you need to pause real quick and do that, that'd be a good idea, and I'm going to go ahead and kind of work through this here. Okay, so one thing I see is you have, for example, grilled chicken. So I'm going to write that as grilled chicken. I'll write GC. I'll write GC right here. Grilled chicken. Awesome. We also have a turkey sandwich. So I'm going to write turkey sandwich. And I have a pasta salad. Those are my main choices. Now, if I choose a grilled chicken sandwich, then I have to pick a side dish. And I can choose from a salad or applesauce. So I can choose from salad, or I can choose from applesauce, right? So if I get this, then I pick one of those. That's true also for the turkey sandwich. I can get salad or applesauce. And also for pasta salad, I can get a salad or applesauce. Okay, so you see how this works so far? From this choice, then I move over here and I have these two choices. Now once I've selected my side dish, then I have to decide which drink. And there are 3 drink choices, right? So once I get my salad, I could get a milk, a juice, or a water. If I got a grilled chicken with applesauce, I could then get a milk, a juice, or a water. If I got a turkey sandwich with a salad, I could also get a milk, a juice, or a water. And if I got a turkey sandwich with applesauce, I can get a milk, juice, and water. And if I had pasta salad, I could also get a milk, juice, and water. Pasta salad applesauce, I can get a milk, a juice, and a water. Okay, now I use abbreviations here because you can see there's a lot to write. So it's just easier than writing the whole thing down. That would take quite a while. So these are some different combinations, right? I can get a grilled chicken sandwich, salad, and a water. I could also get grilled chicken, salad, and juice, or grilled chicken, salad, and milk. If I was to make this a list, I would have something like, I could say grilled chicken, comma, salad, milk. Grilled chicken, salad, and juice. Grilled chicken, salad, and water. I have grilled chicken, and then I can do applesauce and milk. Grilled chicken, applesauce, and juice. Grilled chicken, applesauce, and water. And so you can see I can make a list and continue this, and then I can move to the next one, right? So in terms of my options with grilled chicken, I can see that if I chose grilled chicken as a main dish, I'd have 1, 2, 3, 4, 5, 6 different possibilities when it comes to the side dishes and drinks in terms of their combinations. There's lots of different things that can happen here. Altogether, we can count on the end of our tree. This is a tree, and this one is a list. We can count to see how many choices there actually are, and we can number them here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different outcomes. We have 18 different outcomes that are possible with these 3 options here, which is incredible. That's a lot of different varieties or combinations that could take place. And we see we have 18, which is a result of having 3 main courses, 2 dishes, and 3 drinks. We end up with 18 outcomes. So taking a look at that, if you want to think about it for a second, is there a way to help us determine how many outcomes are possible if we just look at what our options are? Or do we need to write a list or make a tree? The tree definitely shows you all 18. And here in this list you can see I've only written down 6 of them. I'd have to have another 2 columns to make the other 6 happen, which should be combinations with the turkey sandwich and combinations with the pasta salad all the way down, and then their combination of side dishes or drinks. Okay, so we have 18. You can look and have 3, 2, and 3. So we'll come back to this in a second, but we know there's a total of 18. Let's consider the experiment, flip a coin, and then roll a number cube. So think about, I'm flipping a coin, which means I could get a head or a tail, and I roll a number cube, which means I can get a 1, 2, 3, 4, 5, 6. So if I'm doing both of these, right, it's an and thing. I'm doing this one and I'm doing that one. Let's take a look at the different solutions that could come up here, or the different sample spaces that could come up by doing this experiment here. In this experiment, Elena, Kieran, and Priya each use a different method for finding the sample space of this experiment. Elena carefully writes a list of all the options. She flips a head and rolls a 1, flips a head, rolls a 2, flips a head, rolls a 3, flips heads, gets a 4, heads and a 5, heads and a 6, and then she can get tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. Okay, that all works there. Kieran makes a table. You can see here, these are the coin options on this side, right? There are 2 heads and tails, and this is the number cube on this side, which has, of course, 6 there. So the combinations line up like in a table: H in 1, T in 1, H in 2, T in 2, H in 3, T in 3. So it's a little bit of an abbreviated way of showing all the possibilities. When we look at Elena's list, we can count all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them here, 12 outcomes there. We can see in this list that there's 12. We have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. We have 12 outcomes there. Now Priya draws a tree with branches in which each pathway represents a different outcome. So take a look at Priya's. So Priya does it this way. She says, well, let's just draw it like this. You flip a head and you get 1 to 6. You can flip tails and get 1 to 6. And again, you can see all 12 outcomes listed right there as well. When you compare all 3 models, what is the same about each method and what is different? Well, for each method, you are definitely organizing your possibilities. They each list the heads and tails, and they also show that. So the sample spaces all seem to be the same. Each one definitely shows 12 outcomes. That's the same. These are all sample spaces, right? Sample spaces are organized maybe a little differently, whether it be in a table or a tree or just a list. Okay, and then a couple of things we can do. When I think about it, when I look at Elena requires a lot of writing throughout that list there, right? So if I added more things to it, if I had more than 2 outcomes or 2 things to experiment with, and they have multiple outcomes, this list could get really, really long. This table seems to be a simple way of adding to that there, but it does seem limited because I only can put 2 things in there at once. It'd be hard to put a third thing in there. This tree, I definitely can do another branch like we saw in the first thing, right? With the main courses, right? I was able to go 1 item, 2 item, and do a third option there. The tree, I can make a third branch and keep going, so it's not limited by having more options to choose from. So that's a nice part about the tree. Hard part about the tree, as you can see, I start running out of space pretty quickly because it keeps growing, the branches grow. So the question number 2 is, which method do you prefer for the situation? And that's really up to you. There's no right or wrong. It's which one do you like to use when it comes to, if someone said, show me all the sample spaces, which one makes the most sense? Okay. For me, I probably like the tree if I'm going for just the speed of it, just quickly, right? Just doing heads, tails, and then 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. I can see quickly what I have and I can move on. That's easier than drawing a whole table for me and then writing and labeling it, and that just takes longer. This was really quick and simple, but I'm looking for speed. I'm not necessarily being accurate there, but it's just faster. Okay, so that's something to look at there as well. Now notice again that with our outcomes, just something to kind of point out real quick before we move forward, is that I had 2 options for my coin, and then I had 6 options for my my die, rolling the number cube, for a total of 12 outcomes. Okay, so again, interesting to see I have 2 and 6 and I get 12. Isn't that interesting there? What could you do with 2 and 6 to get to 12? Well, hopefully you're saying you could multiply those. Well, 2 times 6 is 12. That's true. The question would be, does that work for everything? Can you always multiply the number of possibilities in each group to find out the total number of outcomes when you combine something together? Let's look back at the very first one real quick. Let's look back over here. Because we had 3 main courses, 2 side dishes, and 3 drinks. What happens if we multiply all of those together? Well, 3 times 2 is 6, and 6 times 3 is 18. Do you remember how many outcomes we had? We had 18 outcomes. So look at that. If you take the number of items you can choose from in one set, multiply it by the number in the second, and then multiply it by again if there's a third, and put that together, that will always tell you the number of outcomes you come up with, or the number of combinations that are possible. So in this case, 3 times 2 times 3 was 18. In this case here, 2 times 6 was 12. Let's keep that in mind as we kind of move forward into the next activity. So this next one, it says find the sample space for each of these experiments using any method. Make sure you list every possible outcome without repeating any. Now this could take a little bit of time, and again you get to decide which method you prefer and which one you want to use. Okay? So in our first one, we're going to flip a dime, and then flip a nickel, and then flip a penny, and record whether each lands on heads or tails or up. Okay? So you can think of it this way. Here's one way of considering this, right? So I have a dime, a nickel, and a penny. Okay? I'm going to draw like this. And I can say the first time I do it, I can do all heads, heads, and heads. The next time I can do a head, and I'm going to add one tail. Then I can do a second time. Let's pretend that this guy gets the tail. So I'm just taking the tail and sliding him over there, and then we'll say now the next time this guy gets the tail. So we can see I have the first one is all heads. This one is one tail. Now let's start with the heads again and say now everybody gets 2 tails. So head, tail, tail. Let's move the H over 1, so we'll have tail, head, tail. And let's move the H over here to have head, tail, tail. And then finally, so we've had no tails, 1 tail, 2 tails, and we're down to 3 tails. So at this point, these are the different combinations that I could have if I'm flipping a dime and a nickel and then a penny and just checking to see if they have heads or tails. In total, we can see that I have a total of 1, 2, 3, 4, 5, 6, 7, 8 outcomes are possible. 8 outcomes are possible. Now, think about your dime, your nickel, and your penny. How many outcomes are there for heads or tails looking at a dime? Well, there are 2. How many outcomes are there for flipping a nickel? Heads or tails? 2. How many outcomes are there for a penny flipping it heads or tails? There are 2. If we multiply those together, what is 2 times 2? 4. And what is 4 times 2? That's going to be 8, which matches our outcomes right there. So if you ever make a list and you want to double check it, you can look this way and say, did I get all 8 possibilities? Let's take a look at B. It says Hans' closet has a blue shirt, a gray shirt, and a white shirt. It has blue pants, khaki pants, and black pants. He must select 1 shirt and 1 pair of pants to wear for the day. So let's take a look here. We can make a little thing, chart. We can make a list. We can make a chart. We can make a tree, whatever you like. I'm going to go to make a tree this time. This is going to be my blue shirt, my gray shirt, and my white shirt. And I can make trees going this way. And I know I have 3 options for the shirt, and I have 1, 2, 3 options for pants. So I'm going to make my pants go like this. And I have blue, I have khaki, and I have black. Blue, khaki, and black. Blue, khaki, and black. So when we're looking at this, what I notice is, in terms of outcomes, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes once again. Well, maybe not once again, but I have 9 outcomes. If I look at my options, how many shirt options are there? There are 3 shirt options. How many pant options are there? There are 3 pant options. And 3 times 3 is 9, which matches the number of outcomes there. Looking at C. We're going to spin a color, then spin a number. All right, well, how many colors are there? Let's work backwards this time. How many colors are there? There are 1, 2, 3, 4 colors. How many numbers are there? 1, 2, 3, 4, 5. So how many outcomes would we expect? 4 times 5 is 20. So knowing that, we have to think about, well, what do you want to make? Do you want to make a list of 20? Or do you want to make a tree? Do you want to make a chart? There's different options here. Let's go ahead and make a list of 20, okay? So I could have red with a 1, red with a 2, red with a 3, red with a 4, and red with a 5. I could have blue 1, blue 2, blue 3, blue 4, or blue 5. I could have green 1, green 2, green 3, green 4, green 5. And I could have white 1, white 2, white 3, white 4, and white 5. So those are all possible sample spaces as well, right? These are all my sample spaces. And you can see I have 1, 2, 3, 4, 5 by 1, 2, 3, 4. And so that's a total of 20 outcomes all together. Okay? So we're good to go right there. Now, in our next one, we say, let's spin the hour hand on an analog clock. So a clock, of course, looks like this. We have 12, 6, 9, 3, 1, 2, 4, 5, 7, 8, 10, and 11. So we have a total of 12 numbers, and then we're going to choose AM or PM. Okay? So in terms of our options, we can make a tree if we wanted to. We can make a list. We can make a table. Let's make a table real quick. So a table, I could have 1, 2, 3, 4, 5, 6. I'm running out of room here. Let me erase that real quick. So when I get a lot, it just gets to be kind of a hassle. Let me closer together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now let's do AM, PM. Let's look at all my possible options here. So we have 1 AM, 1 PM, 2 AM, 2 PM, 3 AM, 3 PM, 4 AM, 4 PM, 5 AM, 5 PM, 6 AM, 6 PM, 7 AM, 7 PM, 8 AM, 8 PM, 9 AM, 9 PM, 10 AM, 10 PM, 11 AM, 11 PM, 12 AM, and 12 PM. So there's my table to show me the same information for how many options I could have, sample space for hour hand and a clock. How many are there? Well, we have 12 times 2, or 12 numbers here on the clock and 2 options there. So 12 times 2 is going to be equal to 24 outcomes. All right. So again, we can see that if I look at how many samples are in each one, or how many options are in each one, if I multiply those things together, it can tell me the total number of outcomes, or the number of things I would have in a sample space. All right, so that's kind of the first part of what we're doing today. Let's apply this to something a little bit bigger. Let's talk about making some sandwiches. All right, so making sandwiches. How many sandwiches? A submarine sandwich shop makes sandwiches with 1 kind of bread, 1 protein, 1 cheese, and 2 vegetables. How many different sandwiches are possible? So how many different combinations can you make? Now let's make a note here. You get 1 bread, you get 1 protein, you get 1 cheese, and you get 2 vegetables. All right? So think of it this way. I could get an Italian bread, I can get tuna, I could get provolone, and then I can get lettuce, and I can get tomatoes. Okay? So those are 5 different things that make 1 sandwich. Now, this is going to be a really long list to write if I keep writing it like that, isn't it? Okay? Now, how many choices are there for bread real quick? There are 3 choices for breads. There are 1, 2, 3, 4 choices for proteins. Cheese has 1, 2, 3, and we're going to include the none. We're going to say that it has 4 choices. Okay? None is a choice. So we're going to make that as a choice, none. And vegetables, there are 1, 2, 3, 4, 5 choices for vegetables. Okay, so in terms of different sandwiches, it says you do not need to write out sample space, so don't write it out. We can see that when it comes to, we have bread, we have protein, we get a cheese, and we get a vegetable, and we get another vegetable. So what do I have? I have 3 choices for bread, 4 for protein, 4 for cheese, including the none, and I have 5 choices for vegetables, and then I have 5 choices for vegetables. The reason it's 5 and 5 is you could do tomatoes. Some of you might be thinking, but if I choose tomatoes, then what happens if I have to get something else? Do I have 4? Well, let's for now say you can double up tomatoes or double up lettuce. That's okay. Maybe at some other point you might say 1 goes away, and that would become a 4. But for now, let's leave it like you get to choose and have double up if you want to. So in this case, based on what we saw before, if I multiply all my options together, that's going to give me my total sample space. That's going to give me my total number of different sandwiches. So 3 times 4 times 4 times 5 times 5 is actually 1,200. Now again, something you wouldn't want to write out as a sample space. That's a lot of different samples, isn't it? Even if you did a tree diagram, that's just way too many. So there are 1,200 different sandwiches that can be made with that menu selection there. Now Andre knows he wants a sandwich that has ham, lettuce, and tomatoes on it. Okay, so he knows for sure he wants that. He doesn't care about the bread or cheese. How many different sandwiches would make Andre happy? So we need to see, okay, well, how many different bread and cheese combinations are there? Well, bread has 3 choices, and cheese, including the none, has 4 choices, which means that there are a total of 12 different ways you can combine bread and cheese to then add on to his ham, lettuce, and tomatoes. 12 different possible ways of doing that there. Okay? So, if a sandwich is made by randomly choosing each of the options, what is the probability that the sandwich that Andre will be happy with? Okay, so if you randomly pick a sandwich, what's the odds that he gets that one of those 12 sandwiches? Well, there are 12 sandwiches that he likes out of the 1,200 sandwiches possible. That's a lot of I'm not sure if that's going to happen. Right? If I reduce this becomes 1 out of 100, or in terms of a probability, we're talking about 0.01. We're talking 1/100th of a chance that it's going to happen. Really, really small chance that whatever they randomly get, it's going to be what he wants. Just kind of how that works there. All right. So, in summary today, sometimes you just need a systematic way to count the number of outcomes that are possible in a given situation. If you suppose, for example, that there are 3 people, A, B, and C, who want to run for president of a club, and 4 different people who want for vice president, so 3 people for president, 4 for vice president, and we wanted to figure out how many outcomes there could be, well, we could look at that. We can make a tree diagram, a table, or a list. And so you see here we can make the tree. We can have person A, B, or C with 1 of 4 vice presidents there. You can have it with, you put the VPs first, and then the 3 presidents there. You could do a table and have A, B, and C, and 1, 2, 3, 4, and see all the different combinations, or you could make the list like you see down here. Overall, though, it's important to remember that if I take the number in each group, 3 and 4, if I multiply those 2 numbers together, that's going to give me the total number of outcomes that are possible. Whether I see it here in the table, 12 there, or I simply count up that list and recognize there are 12. That's the shortcut way of figuring out how many different ways are actually possible. So we're going to pause there, let you work on your homework. We'll come and check that together in just a minute. Alright, homework time. Noah's planning his birthday party. Here's a tree showing all the possible themes, locations, and days of the week he's considering. Alright, so how many themes is he thinking about? Well, we can see the themes are here. Right, in this space right here. We can see 1, 2, 3 themes he's considering. For locations, that's right here. And we can see he's considering skating ring, park. Do we count these again? No, these are the same ones. Skating ring, park. We just count the 2. Don't count them again. Those are the same locations. So there's 2 locations. And the days of the week, we can count them here. And we can see we have Friday, Saturday, Sunday. It's the same all the way down. Those aren't different days. It's the same 3 days he's considering. So he's considering from 3 themes, 2 locations, and 3 days. One possibility that Noah is considering is a party with a space theme, skating rink on Sunday. Right, 2 others. Sure. He could be considering a safari at the park on Friday. Okay, so just think about safari, park on Friday. That's a possibility. So you can think of another one as well. Now, how many different possible outcomes are there? Well, there are 3 outcomes for the theme, there are 2 possibilities for location, and there are 3 possible days. So 3 times 2 is 6, and 6 times 3 is 18. So there are 18 different outcomes that are possible, which you can see if you followed each one and said that this was one outcome by itself, right? Let's go with space to skating rink to Friday. That's one outcome. There's one there, and we can see 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 right there. All right, number 2. For each event, write the sample space. Remember, sample space are all of the what? The possibilities, and tell how many outcomes there are. So Len selects 1 type of lettuce and 1 dressing to make a salad. We can see iceberg and romaine lettuce, and we can see ranch, Italian, French. So in terms of the outcomes, we know that there are 2 lettuce types and there are 3 dressing types, which means I'm going to have a total of 6 outcomes. Now for my sample space, let's use some abbreviations here. I can write it out. I can write it as a list. I can write it as a tree. Doesn't make a difference here. I'm going to do a tree this time. I'm going to do iceberg, and I'm going to do romaine. And iceberg can be paired up with ranch, Italian, or French dressing. And the romaine can be paired up with ranch, Italian, or French dressing. Those are my sample spaces. If you want to make a list, you could. You could do Italian with ranch, iceberg with ranch, iceberg with Italian, iceberg with French. You can do romaine with ranch, romaine with Italian, and romaine with French. There's a list as well. If you want a table, you can do that too. Okay, Diego chooses rock, paper, scissors. Jay chooses rock, paper, scissors. All right, so what are my options? Well, you can have a rock and a rock. You can have a rock, he can have a rock and she can have paper. He could have a rock and she could have scissors. Or he could have paper and she has a rock. He could have paper and she has paper. He could have paper and she has scissors. Or he could do scissors and she gets a rock. He can have scissors, she gets paper, and scissors and scissors. So, how many options are there? I see 1, 2, 3, 4, 5, 6, 7, 8, 9 outcomes. Does that match up? Well, 3 times 3 equals 9 outcomes. Okay. All right, look on the next page. We'll look at 3 spinners. Here we go. So we're going to spin some spinners here. And once again, what do we see? We have 2 options here, 2 options here, and 3 there for a total of how many outcomes? 2 times 2 is 4, and 4 times 3 is 12. So we have 12 outcomes. Can I write this down? Sure. Let's make a big tree. Let's go with B, and let's go with M for the first one. After you spin a B or an M, you can get an A or an E. So we can do an A, and we can do an E, we can get an A, and we can get an E. And then from there we get D, N, T. So D, N, T, D, N, T, D, N, T, D, N, T. And we can add those in there just like so. And those are my tree diagram and all the sample space that would be available. All right, number 3. A simulation is done to represent kicking 5 field goals in a single game with a 72% probability of making each one. A1 represents making the kick, A1 represents making the kick, and a 0 is missing. Okay, so making is going to be with a 1. So when I look over here at trial 1, we can see 1, 2, 3 made kicks out of 5. Over here, I can see that there are 1, 2, 3 made kicks out of 5. In the third trial, we had 2 made kicks out of 5. The fourth one, we had 5 made kicks out of 5. And the fifth one, we had 3 made kicks out of 5. So based on these results, so what you see right here, just looking at here, all that, estimate the probability that 3 or more kicks are made. So what is the likelihood that 3 or more kicks are made? We see it happening 1 time, 2 times, 3 times, 4 times. So based upon our trial, we would say the odds of probability of making 3 more kicks is 4 out of 5, based upon what we see. And finally, number 4, I think the last one here, yep. There are a bag of 50 marbles. Andre takes out a marble, records its color, puts it back in. In 4 trials, he gets a green marble 1 time. So he gets 1 green out of 4 tries. Jada takes out a marble, records its color, puts it back in. So in 12 trials, she gets a green marble 5 times. So she got 5 out of 12. Noah takes out a marble, records its color, puts it back in. In 9 trials, he got 3. So he got 3 out of 9. Estimate the probability of getting a green marble from this bag. Explain your reasoning. Well, if I look at all of what they did, they got green a total of 5, 6, 7, 8, 9 times they got green out of how many tries? 12 plus 9 plus 1 is 25. So in all, if you add them all together, they got green 9 times out of 25, which is about 0.36. So the probability of getting green from this bag is about 0.36 or 9 over 25. However you want to write that, both answers would be acceptable, and explain your reasoning. Okay, that's it for today. Have a great day. We'll see you next time.